In the fall of 2016, a team of astronomers monitoring the outer edges of our solar system noticed something, a faint point of light, far beyond the orbit of Neptune, moving in a way that didn't quite fit. The initial observations were easy to dismiss. Instrument noise, a glitch in the data reduction pipeline. But when 3 separate observatories confirmed the same coordinates, the same inexplicable motion, something shifted in the room. This wasn't error, this was real. NASA found an object near Neptune with properties that defy every model of our solar system, and after 8 years of silence, we still don't fully understand what it is. If you enjoy these deep dives, you can subscribe. It helps more than you think. So, let's begin. The object was catalogued under a provisional designation that most people will never hear. Not because it's classified, but because the scientific community hasn't agreed on what to call it. Discovery announcements are usually straightforward. You find something, you measure it, you publish, but this one sat in internal review for 19 months. That alone should tell you something. The first detection came from a long exposure survey designed to catch Kuiper Belt objects, small, distant, cold. The kinds of things that have been out there since the solar system formed. Rocks and ice, leftovers from planetary construction. We've found thousands of them. We know what they look like. We know how they move. This wasn't one of them. The light curve was wrong. When an object tumbles through space, its brightness changes in predictable ways. Shape, rotation, surface texture. All of it leaves a signature. This object's brightness flickered with a rhythm that implied rotation, yes, but also something else. The variations were too sharp, too fast, and they didn't repeat cleanly. Every orbital model tried to fit the data broke down within weeks. Brightness in astronomy is everything. It tells you size, distance, composition, reflectivity. If you know how far away something is and how much light it's giving off, you can calculate what it's made of. Rock is dark, ice is bright, metal, depending on oxidation, falls somewhere in between. This object reflected light like it was covered in fresh frost. Albedo, near 0.9, which is almost unheard of. That's brighter than Europa, brighter than Enceladus. But the infrared signature didn't match at all. When you look at something cold and distant in infrared, you're measuring heat. Reflected sunlight is one thing, thermal emission is another. The object's temperature, as measured by multiple instruments, was far too high for something that reflective and that far from the sun. The math didn't close. If it was icy, it should have been colder. If it was warm, it shouldn't have been so bright. The spectral lines, the fingerprints of chemical composition, showed water ice, yes, but also absorption features that didn't correspond to any known mineral or volatile compound in our catalogues. Then there was the orbit itself. Most objects in the outer solar system follow elliptical paths that make sense. You can trace them backward, see where they came from, predict where they'll go. Gravitational dynamics are clean out there, predictable. This object's orbital eccentricity, the measure of how stretched or circular its path is, changed, not over millions of years, the way it should under planetary perturbations, over months. That's not supposed to happen. Not unless something is pushing it, and there was nothing there to push. Teams ran simulations, gravitational interactions with Neptune, with Uranus, with hypothetical distant planets. None of it worked. The object wasn't following a bound orbit in any stable sense. It wasn't following a hyperbolic escape trajectory either. It was something in between, something that required either a propulsion force we couldn't detect or a mass distribution that violated basic physics. The mass was the next problem. You can estimate mass from gravitational influence, from how an object bends space-time around it, from how it perturbs nearby bodies. When observatories tried to measure this, they got contradictions. The object's gravitational signature suggested something small, maybe 100 kilometers across, but its brightness and the way it occluded background stars suggested something much larger or much stranger in shape. A highly elongated body, perhaps. Except, elongated bodies tumble predictably, and this one didn't. Some researchers proposed it was a contact binary, 2 objects stuck together, rotating around a shared center. That can produce weird light curves. But contact binaries don't change their thermal output, they don't shift orbits, and they definitely don't emit radio waves. The radio emissions were discovered by accident. A deep space network array was tracking a different object in the same region and caught a transient signal, faint, irregular, but undeniably there. Follow-up observations confirmed it. The signal wasn't constant. It pulsed, not like a pulsar, not with that kind of regularity, but with a periodicity that almost matched the object's rotational light curve. Almost. The phase was off by a few degrees, drifting over time. Engineers checked the instruments twice, 3 times. The signal was real, and it was coming from the object. Natural radio emissions exist. Jupiter makes them. Magnetospheres interacting with solar wind, charged particles spiraling through magnetic field lines. But this object was too far away, too cold, and showed no signs of having a magnetosphere. There was no plasma environment to generate that kind of emission. It was just there, quiet, persistent, wrong. By 2018, the object had passed its closest approach to Neptune and was heading outward. Mission planners proposed a flyby, a fast probe, something already in development, rerouted to intercept. The trajectory was doable, expensive but doable. Then, the object changed course again, not dramatically, just enough that every recalculated mission profile came back with fuel margins too thin to risk. The window closed, and the object kept moving. More observatories joined the effort, ground-based telescopes in Chile, Hawaii, South Africa, space-based infrared platforms. Hubble took a look, so did some of the newer exoplanet hunting satellites, repurposed for solar system work. Every dataset added more confusion. The object's spectral signature shifted between observations, not like surface weathering, like the composition itself was changing. Water ice 1 month, then something with carbon chains, then back to water. Astronomers started using the word metamorphic, which doesn't make sense for a frozen rock in the outer dark. One team proposed the object was venting, outgassing, like a comet, except it wasn't near the sun. It wasn't warm enough to sublimate ice in the volumes required to explain the orbital changes, and there was no visible coma, no tail, no particle cloud. Sensitive detectors found nothing. If it was venting, the material was invisible, which raises more questions than it answers. Another hypothesis involved subsurface oceans, tidal heating from a moon we hadn't detected, generating warmth, creating cryovolcanism. But there was no moon. Repeated surveys, multiple wavelengths, found nothing in orbit around the object. It was alone, and tidal heating requires a companion. The physics won't allow it otherwise. The gravitational anomalies deepened with better data. When you measure an object's mass precisely, you use its effect on nearby bodies. There were no nearby bodies. Neptune was too far away for meaningful perturbation. Some astronomers tried using background quasar positions, measuring the object's gravitational lensing as it passed in front of distant light sources. The results were inconsistent. Different measurements gave different masses, not by a little, by orders of magnitude, as if the object's mass was fluctuating, which is impossible. Mass doesn't just change, not without releasing energy, a lot of energy. If the object was somehow converting mass to radiation, we'd see it. Gamma rays, X-rays, something. We saw nothing, just the faint reflected sunlight, the odd thermal signature, and that persistent drifting radio hum. By 2020, internal memos started circulating. Not public papers, not press releases, emails between senior researchers, careful language, a lot of conditionals. The tone was strange, not excited, the way scientists usually are when they find something new, cautious, unsettled. One senior planetary scientist, someone with decades of experience, wrote that the object represented either a failure of observational technique on an unprecedented scale or a gap in fundamental theory. Neither option was comforting. The phrase unknown natural phenomenon started appearing in draft papers. A hedge, a way of saying we don't know without saying we don't know. Reviewers pushed back. They wanted mechanisms. They wanted models, but no model fit. Every explanation required invoking something we'd never seen before. A new kind of ice with properties we didn't understand. A new kind of mineral formed under conditions that don't exist in the solar system. A captured, interstellar object with an interior structure unlike anything predicted. None of it was satisfying. One researcher, working independently, suggested the object might be a fragment of a much larger body, something that broke apart in the deep past, perhaps during a collision. Fragments can have strange rotations, strange shapes, strange thermal properties if their interiors are exposed, but fragments don't emit radio waves, and they don't change orbits without a reason. Another team looked into whether the object might be an extreme trans-Neptunian object, something from the scattered disk, kicked outward by Neptune billions of years ago. Those objects have weird orbits, high eccentricity, high inclination, long periods. But even the scattered disk has rules. Orbits are chaotic, yes, but they're predictable chaos. This orbit wasn't. It was as if something was steering. The rogue planet hypothesis came up. A small, dark planet, ejected from another star system, passing through ours. Interstellar objects exist. We've seen them. Oumuamua in 2017, Borisov in 2019. Both strange, both brief, but both followed hyperbolic trajectories, in and out, fast, never to return. This object wasn't leaving. It was looping, drifting, changing, almost as if it was deciding where to go next. Some astronomers quietly started calling it an orphan. Not a planet, not a moon, not a comet, just something that didn't belong, something the solar system didn't make, but also didn't expel. The data suggested it had been there for a while, years, maybe decades, hiding in the noise, too faint, too far, too strange to notice until we looked closely enough. Telescope time is precious, competitive. You don't get to stare at one weird object forever. Observations became sporadic. Graduate students moved on. Funding shifted. The object faded from the priority list, not because it stopped being interesting, because no one knew what to do with it. Every observation raised more questions. Every paper draft ended with the same weak conclusion. Further study required. In 2022, a new infrared observatory launched, more sensitive, wider field. One of its early phase surveys swept the region where the object should have been. It wasn't there, not where predictions said, not anywhere nearby. Teams recalculated. Maybe the orbit was more perturbed than they thought. Maybe it had moved behind Neptune, temporarily hidden. They waited, checked again 6 months later, still nothing. For a while, there was concern it had been lost. Space is big. Faint objects disappear all the time, especially if their orbits are uncertain. But then, in late 2023, a different survey caught it. Farther out than expected, fainter, colder. The light curve had changed again. The radio emissions had stopped, or maybe just dropped below detection threshold. It was still there though, still moving, still wrong. The current data suggests the object is now beyond 50 astronomical units, twice Neptune's distance, drifting outward, slowly, into the Kuiper Belt's outer edge. Its trajectory is still not fully understood. Some models say it'll continue outward, eventually leaving the solar system entirely over the next few thousand years. Others suggest it'll swing back, loop around, return to the inner system in some distant epoch. No one knows. There's been talk of a dedicated mission, a probe designed specifically to chase it down, match its velocity, take close-range measurements. The engineering is brutal. The object's orbit is inclined, eccentric, and uncertain. Intercept windows are narrow and decades apart. Costs would be immense. Funding, in the current climate, is unlikely. So, the object drifts, and we watch from a distance, piecing together fragments of data, trying to build a picture that makes sense. The physics community has mostly stayed quiet. A few papers have been published, but they're cautious, technical, hedged with disclaimers. The object is described as anomalous, unusual, worthy of further investigation, but no one wants to say what they're really thinking, that we might be looking at something we don't have the framework to understand yet, that our models of how solar systems work, how objects form and evolve, might have a blind spot we never considered. It's not that the object is impossible, it's that it exists in a space between categories, too active to be a dead rock, too cold to be active, too massive to be so bright, too light to bend space-time the way it does. Every measurement contradicts another, and the simplest explanation, that we're making systematic errors, has been checked and rechecked. The errors aren't there. The contradictions are real. Some astronomers have started wondering if the object is a test case for physics we haven't written yet, modified gravity maybe, or quantum effects on macroscopic scales, or something about how matter behaves in the deep cold and deep silence of the outer dark that we've never encountered before. It's speculation, yes, but informed speculation. The kind you entertain when the data won't let you do anything else. The psychological weight of it is strange. Most astronomical mysteries are distant, other galaxies, other epochs. This is here, in our solar system, something we could, in theory, reach, something we could touch, and we don't understand it. That realization sits differently. It's closer than ignorance about black holes or dark matter. It's a reminder that even our local neighborhood, the space we've been studying for centuries, still holds things that don't fit. Mission planners keep the object on a list, low priority but not forgotten. If technology advances, if propulsion improves, if funding climates shift, maybe we'll go. Maybe, in 20 years or 30, a probe will make the journey. Instruments will scan its surface, measure its mass directly, sample its composition, map its magnetic field if it has one. Maybe we'll find answers, or maybe we'll find more questions. Maybe the close-up data will be just as contradictory, just as strange as what we've seen from afar. There's also the possibility we never find out, that the object drifts beyond our reach, beyond our ability to study it, and becomes just another unsolved problem in the catalogue. Astronomy is full of them, things we saw once, briefly, and never figured out. This might be one of them, a footnote in the history of solar system exploration, a puzzle left for future generations, assuming they remembered to look. It's humbling, in a way. We've sent spacecraft to every planet. We've landed on comets, touched asteroids, flown past Pluto. We've mapped the cosmic microwave background, detected gravitational waves, photographed black holes. And yet here, in our own solar system, barely beyond Neptune, there's something we can't explain, something small enough to fit in a city, but strange enough to defy everything we know. The object doesn't care that we don't understand it. It continues its orbit, or its drift, or whatever it's doing. The radio silence, if that's what it is, might be permanent, or it might return. The thermal glow might stabilize, might fade, might spike again. The orbital changes might continue, unpredictably, or they might settle into something we can finally model. We'll keep watching, that's what we do. But there's a deeper discomfort beneath the data, a sense that our picture of the solar system, refined over centuries, might still be incomplete in ways we haven't imagined. That the categories we use, planet, moon, asteroid, comet, might not cover everything that's actually out there. That nature, indifferent to our classifications, has produced things we don't have names for yet. The object near Neptune is one of the most puzzling findings in outer solar system history, not because it's large or dramatic, but because it's quiet and persistent and wrong in ways that don't resolve with more data. Every answer leads to another question. Every measurement adds another layer of confusion, and the scientists who study it, who spend years staring at spectra and light curves and orbital plots, are left with the uncomfortable awareness that sometimes the universe just doesn't make sense yet. Maybe it will. Maybe someone will have an insight, a breakthrough, a new theory that ties everything together. Or maybe this is what discovery actually looks like most of the time. Not sudden clarity, but slow, grinding confusion. The realization that understanding isn't a straight line, and some things take generations to figure out. For now, the object drifts outward, faint and cold and strange, a point of light in the dark, moving in ways we can't predict, reflecting a brightness we can't explain, emitting signals we can't interpret. It's there, it's real, and we don't know what it is. That's the truth of it, the uncomfortable, unresolved truth. We are still learning what exists in our own solar system, still finding things that challenge what we thought we knew. And perhaps that's the most important lesson, that the unknown isn't just out there, in distant galaxies or alternate dimensions. It's here, close enough to see, if we look carefully, too far to touch, too strange to ignore. The sky is full of things we haven't noticed yet, and some of them, when we finally do, won't fit into any box we've prepared. They'll just exist, stubbornly, impossibly, quietly, waiting for us to catch up, or waiting for nothing at all.